So we're going to talk about secure search on encrypted data, how we can do it without setup, without post-processing, and faster than previously. And this is a joint work with Adi Akavia, Craig Gentry, and Shai Halevi. So let's first talk about what do we mean when we say secure search. Suppose Alice has a data array that is unsorted, and its elements are not necessarily distinct. She wants to outsource the storage of this array to SpongeBob Web Services, and later she wants to issue queries and to be able to retrieve the matching elements. She wants the communication and her complexity to be polynomial in the size of the query and the size of the output, and she wants it all to be done in a single round. Her privacy concerns are against a semi-honest, computationally bounded adversary controlling the server, and she wants to hide from the server the data array, issued queries, retrieved elements, search pattern, and access pattern. And the only thing that she's willing to leak is general size information. Her weapon of choice will be fully homomorphic encryption. So suppose she has a message and she wants to delegate the computation of some function f on this message to the server. She can encrypt this message, send it to the server. The server can then homomorphically evaluate the function f on the encrypted message, retrieve the result, return it to her. Now she decrypts it and obtains a result. The benefits in using fully homomorphic encryption is that it allows us to do everything in a single round. The message and the result stay hidden from the server. We have low communication where only the encrypted message and the encrypted result are being transmitted, and we have low client computation here, where only the client needs to encrypt the message and decrypt the result. How we compute over a fully homomorphic encryption ciphertext? Well, we first take our function and model it as a polynomial over some finite ring. For example, over binary, additions will be XOR operations, multiplications will be AND operations, and now we replace addition and multiplication in the polynomial by its homomorphic analog in the scheme. The complexity considerations will include the fact that additions cost us much less than multiplications, and in fact, high polynomial degree will be very expensive for us. So our goals will be to model our solution as a polynomial of low degree with low amount of overall multiplications. The prior state-of-the-art solution that presented the first secure search construction that attained all the desired properties that we mentioned was Spirit by Akavia et al. From last year. And there the server's complexity was polylogarithmic in the degree of the polynomial was polylogarithmic in the size of the array, and the overall multiplications were polynomial in the size of the array. Still, the protocol, their Spirit, had few drawbacks. The deterministic variant had post-processing in order to get the final result and for the result to be error-free. The randomized variant there had a noticeable error probability, and both variants required working over plaintext spaces of GFP for p bigger than 2. So now I want to present our construction, which we call binary ruffle, and let's begin by stating what are our advantages. So first, binary ruffle overcomes the above drawbacks that we mentioned and simultaneously achieves both post-processing free client and an answer that is correct with overwhelming probability. Next, this allows us to do a non-interactive use of this protocol as some subcomponent in a larger computation done by the server. The straightforward example is a single round secure search with subsequent element update. Additional advantage here is that binary ruffle requires operations only over binary plaintext. So this is faster and has a wider compatibility among FHE schemes and other different solutions. The way that we model the matching criteria is by a function that we call isMatch that retrieves two elements and returns a binary result whether those two elements are considered matching in the general settings of our problem. And it can have a versatile domain-specific functionality. I will not go into this. You can read more about it in the paper. But the only thing that is interesting for us that it is modeled as a polynomial with degree d and overall multiplications mu. So our protocol, binary ruffle, is faster among post-processing free protocols. And for example, compared to the randomized version of Spirit, it reduces the server's polynomial degree from cubic to linear in log n. It reduces the server's polynomial degree from linear to logarithmic in 1/epsilon. And it reduces the server's overall multiplication by an additive factor of n log n. If we compare a binary ruffle with a client probability amplification and compare it with a protocol that has post-processing, the deterministic version of Spirit, so we get that we reduce the server's polynomial degree from cubic to linear in log n. We reduce the overall multiplication by a factor of O tilde of polylog n over epsilon. And we are correct with the disadvantage here is that we are correct with overwhelming probability compared to the deterministic version in Spirit where it's correct with probability 1. I want to discuss for a minute about what it means to be setup free. So here and in Spirit and in binary ruffle, in both protocols, the server's complexity is linear in the data array size in n. But if we think about it for a second, this is something that is inherent in setup free scenarios even on clear text data. So we cannot avoid it even on clear text data. And I want to convince you that nonetheless, setup free is still well motivated by many use cases that are detailed in the paper. Now let's dive into the construction of the binary ruffle protocol. The protocol outline will begin by a standard initialization phase where the client generates a public key and a private key, sends the public key to the server. Then the array is uploaded by the client after it is encrypted. And first, the secure search begins by the client encrypting its query and sending it to the server. The server then executes the search algorithm over the encrypted array and the encrypted query and returns the following elements: I star, which is the first match index, encrypted, and the element and this index. So now the client decrypts and obtains this first match and the element that is associated with it. Next, we're going to see and we're going to focus on the step of how we compute I star, because once you obtain I star, you can easily compute and return the element, for example, using peer methods or other methods that we state in the article. So let's dive into how we compute I star. Here, what the server needs to do is he first needs to apply the matching criteria over all the elements and the query. And he needs to get binary vector of indicators. This is, of course, everything here is encrypted here. Now, the server transforms this indicators vector into a step function vector. Next, he computes a pairwise difference of adjacent indexes in this step function vector, where you can see that the I star element is the only single one that will remain. He can utilize this vector d to calculate and return the binary representation of I star to the client. Everything is quite straightforward here, except the second step, how we transform the indicators vector into a step functions vector. So let's dive into this. Our first try will be to compute the logical OR of the indicators vector v. But the immediate problem here is that the polynomial that we get here is of degree n. And this is too much for us in most use cases, so let's try and reduce it. Our approach will be to compute a low degree approximation of the logical OR function. This is a method suggested by Razborov and Smolensky back in the days. And what you do there is you compute the parity of the sum of random subsets of your initial vector v, of the indicators vector. And now you compute the logical OR between all those parity vectors that you received. The key property here is that the probability that the actual OR function and the approximate OR function will be different is quite low, and we are correct with overwhelming probability when big N equals log of small n over epsilon. So we achieved here a logarithmic degree. We tested our protocol and we implemented it over a HELIB C++ FHE library. We ran it on a medium-sized server. We tested it on several is-match functions, but I want to show you the results regarding the binary equals, the simple binary equals function. So what you can see here is that the time here is in minutes and the array size is in millions. And we compare it, the binary raffle protocol with a negligible error probability, a really small error, compared to the deterministic version of Spirit for words of size 1 and size 16, where I want to mention that words of size 1 is as if we performed the matching criteria offline, for example, by pre-computing the indicators vector before sending it to the server. You can see in these graphs that the binary raffle protocol is faster in several orders of magnitude compared to Spirit. And also, we got RAM exhaustion in Spirit as the array size rised. If we look at the binary raffle protocol with error probability half, a small error probability, and compare it with the randomized version of Spirit, so again, we see that binary raffle is faster in an order of magnitude, and we have RAM exhaustion in Spirit as the array size rises. If we look at the impact of the error probability on the runtime, we performed several experiments with different error probabilities, and we indeed verified that there is a logarithmic dependence in 1 over epsilon for both the degree and overall multiplications, as we stated it previously in the equations that we've seen. And in a similar manner, the impact of the word size, here the word sizes are of 1 bit and 64 bits. Again, we see a linear dependence in the word size for the runtime and its effect on the degree and overall multiplication. In the article itself, we also presented many additional extensions. For example, added functionality of how we can retrieve additional elements except the first element. How we can do dynamic data management, for example, doing updates, doing deletes, and inserts. We presented the ability to plug in versatile matching criteria. For example, how we can do Boolean logic queries, wildcard queries, searching in subarrays, and so forth. And we presented several optimizations. For example, how we can do a faster exact matching with a tool that is universal hashing plugged into the matching criteria. And also how we can do client-side amplification of as an optimization. I really want, in a nutshell, to present related methods to this work. And you can find in the paper more details that compare this work with all these works that I'm presenting here. For example, there we have private information retrieval, but the difference here is that it's not actually search, because in peer, client must know the unique identifier of the element. There are many methods that require setup. For example, searchable encryption, peer by keywords, searchable encryption and ORAM. And here we presented a method that does not require setup. There are also many common searchable encryption schemes that deliberately leaks some information to enable search, as compared to our solution that doesn't leak anything except the higher bounds of the sizes. And here I want to present the exception of searchable encryption and ORAM that does not deliberately leak much information. And let me jump to the conclusions. We presented here a secure search protocol over FHE encrypted data and query, where we have a single round, single server. It's setup free. The client complexity and the server's complexity is as promised. We have a faster implementation than a previous scheme for secure search, wider compatibility, and many extensions. Thank you very much, and I would gladly take questions.
Any questions? Nobody wants to ask a question? Really? Yes. I'll give you the mic just for the... Ryan,
nice talk. So one quick question. So you have, on your experiment, you have some false positive rates. What?
Sorry?
Some false positive rate. Like on your experiments, like, yeah, here you have an error probability here, epsilon, and in like
here.
How does? Okay, my blame. I didn't see the graphs. So, do you think that actually reducing a lot, like playing a lot on the error probability, really helps, not only in your construction but on other constructions?
In our construction, because there is, as mentioned here, a logarithmic dependence in 1 over the error probability. So we've seen that regarding the runtime, there is a difference, but it's not much considerable, and you can, for example, replace the high error probability with small error probability and do parallelization, for example, with a small error probability and achieve almost the same results. So here, even for error probability half, you receive good results, and these results can be augmented as you like, with parallelization, without parallelization.
Yeah, so I just wanted to mention, so most searchable encryption schemes nowadays are forward private. So they're dynamic and forward private, which means that you don't really need setup. So it's achievable with searchable encryption with common schemes.
Thank you.
Any other questions? It looks like an Ian question.
Thanks. So your error probability is coming from the low degree or approximation, is that right?
Yep.
So is the error, like what happens if there's an error? Is it only in one direction, like you'll miss an element you should have matched, or you'll match an element you should have missed? Or
It's only in the direction that you missed the first element and you might have received the next one.
Okay.
Not the first one. So you can always, if you have a high density array with lots of repetitions and you don't care about whether you get the first one or any element, you simply get the next one.
Right. Okay, thanks.
Any last quick question? Okay, then let's thank Max again. Next talk is by Ryan about, and this is going to be a bit tricky, a bit more than a bit is more than a bit better, about faster PIR. So Ryan, take it away. Thank you.
You're a brave man, voter. Yes, so I am indeed presenting a paper with a tongue twister for a title. I will try to say it again as well. So the paper title is A Bit More Than a Bit is More Than a Bit Better, Faster, Essentially Optimal Rate, Many Server PIR. In fact, it's actually the second half that's harder to say than the first half, which is weird. And I think now that I've read that title, I'm probably out of time. So I will just wrap things up and say, in conclusion, you should read the paper. It's great. And 17 words is tad excessive for a title, just for future note. No, actually. let's go back to this title. So there actually is a lot going on in this title. I'm going to spend the first part of the talk just sort of unpacking this title a little bit, or at least this title slide. So to start with, I am Ryan Henry. I'm a professor now at University of Calgary, technically still at Indiana University. My student Syed unfortunately couldn't be here. He would love to have been here because, especially right now, he's going to be on the job market right away, and you should definitely hire him. But alas, you have to suffer through me and my terrible sense of humor instead of getting to listen to Syed. Okay, so back here. So what else do we have to look at in this title? So I'm sure many of you know what PIR is, but we'll start there. So PIR stands for Private Information Retrieval. This is a pretty fundamental cryptographic primitive. It allows a user to send a request to a database. Once the database has received the request, the user waits for quite a long time, apparently, and eventually gets a reply back. And what's special about PIR versus regular information retrieval is that in exchange for this excessive waiting time, the client has retrieved a record from the database, and the database learns nothing about what it was that the client asked for or got from the database. So you can imagine lots of places where this would be useful. It's often not used in practice because of that excessive waiting, among other things. Okay, what else do we have in this title? So many server comes in the title. So this refers to the style of PIR protocol we're talking about, usually called multi-server PIR protocols. So the idea is the client sends a request to the servers, to multiple servers that each hold, say, a copy of the database or something like it. You'll notice the clock went a little faster there because multi-server PIR tends to be faster than other single server PIR protocols. And then once those servers respond, the client is going to be able to take what it learned from them, put it all together somehow and learn its desired data, and is going to have privacy against those servers, provided the servers don't collude. And there's various different assumptions about what exactly constitutes collusion. It could be all the servers, it could be just a couple of servers. And in this title, I used many server instead of multi-server, and that's because we're specifically looking at what if you have a ton of servers at your disposal, what can you pull off? So our protocols will work fine with just a few servers. If you have only 2 servers, we have nothing particularly interesting to say because our protocol ends up being equivalent to well-known results. But as the number of servers grows large, things get kind of nice. Okay, what else do we have here? So it's faster. What I mean by this is basically the amount of time it actually takes to make a query is really quite fast. So before we had this picture of you send a request, the clock ticks and ticks and ticks. And what we're going for is something more like this. We have a bunch of servers, you send the request, the clock goes super fast, the result comes back, and everything's done. Yeah. And few more words. Okay, so essentially optimal rate. So basically what this is saying is that the download cost of this protocol should be really low as possible. The word essentially shows up there because there's some ceilings and stuff in the equations. If you ignored the ceilings, then you could prove that to the bit, you can't do better than this. With the ceilings, it's not really clear whether maybe you could shave a bit or 2 off the communication cost, but you certainly can't shave more than, say, 1 bit per server, which is kind of awesome. So going back to our diagram from before, we still have the super, super fast clock, but now the responses that we get back are all pretty small, and when you put them all together, you get something that's basically comparable in size to what you're trying to fetch. In traditional multi-server PIR protocols, what you get back is from each server is about the size of the record you're looking for, perhaps even a little bit bigger, and we're trying to go for what you get back when you sum up all the servers is about the size of the actual data. Okay, so only a few more words left. So the tongue twister on the left side, this is referencing the paper that this all started from. So this paper, 1 extra bit of download ensures perfectly private information retrieval. I saw this paper and I thought that's an intriguing title. I read the paper and I thought, I don't quite understand what's going on here. So I read the paper more carefully and spent some time going through it and wrapped my head around what was going on and realized that by taking what these people have done, modifying things in relatively modest ways, we can get quite practical protocols, and then from there we did some even more interesting stuff to make the protocols even more practical, but it all sort of starts with their construction and just does some massaging to it, generalizations, etc. So rather than having one extra bit of download overhead for private information retrieval, we're going to have a bit more than 1 bit, and it will be more than a bit better. I love cheesy titles, I'm sorry. Okay, so I think that's it for the title slide. So rather than jumping into what we did, I'm going to jump into how awesome what we did actually is in practice. So here we've got a plot, and I'm going to show the 2-server version of our protocol. So this protocol, for those of you that have seen multi-server PIR, is effectively just the original PIR protocol from Chor, Gilboa, Kushelowitz, and Sedan, I think, yeah. So this is what we had for our implementation of that in this scheme. It's actually quite fast. This was a 256 gig database on the right-hand side, or I guess my left hand, your right-hand side. And we're managing to chug through that at like 5.69 gigabits per second, which isn't so bad. So it only takes, a handful of seconds to get through this entire query. And as we increase the number of servers, we see some pretty nice speed ups. So a lot of papers seem to take for granted that you really can't beat that protocol, but we find that actually you can beat that protocol quite a bit. So when we have 2 servers, we basically double the speed of the protocol. By the time we're up to 64 servers, we're getting like 144.7 gigabytes per second throughput, so we can actually do a query over this 256 gig database in just under 2 seconds, which is fast enough that people might actually do that. So how does this compare to other things in the literature? So I'm going to pick on Ian here, because Ian's the primary author of sort of the standard PIR implementation. So Percy++ implements a bunch of different protocols, and it is generally treated as the benchmark in literature. So this is the same protocol as our slowest line, which also happens to be Percy's fastest mode. Percy's version deals with multiple servers and has a bunch of extra stuff going on, which is why there's such a discrepancy over here. And as the database gets big, the lines basically converge. Ours is marginally faster than the implementation in Percy, but nothing too significant. And then the other modes of operation in Percy get progressively slower from there. Now, it's not a completely fair comparison to compare these things, because as I'll get back to later, there are things that make our protocol not as awesome as I'm claiming it is at this point. And there are things that make the various Percy protocols quite awesome. In particular, these protocols have lots of different knobs you can tune to tune things like what happens if servers misbehave or don't respond. Can you still recover from this? How many servers can collude with one another before privacy is lost? These versions up here, well, this one maybe, and versions with bigger numbers there, can be turned into what's called symmetric private information retrieval, so that the database gets some notion of privacy against the user, and none of that stuff applies here. But if you just look purely at the running times, these are awesome in comparison. Okay. So yes, now let's look at a different set of PIR protocols in literature. These are probably the most closely related. So it's a paper called RAID PIR and an accompanying implementation. It is also highly tunable, but if you tune it, if you set the different parameters to get protocols with analogous properties to our protocols, then we also see nice speedups. So this is when you have 4 servers. Their 2-server version is almost the same as ours. The lines are overlapping, so it wasn't interesting. The 4-server version, in the middle here, I don't really know why we see such a bigger speed up. By the end, we've converged to like a 1.3x speed up for the 256 gig database. And then as you look at larger and larger numbers of servers, that gap continues to grow. So we get nice performance enhancements over prior work. Okay. And this is just the server-side computation cost. So this is, each server is doing this much work. They're all doing it in parallel. So this is effectively how long the client has to wait for the server to do its thing. But that's really only half the story. And in fact, that's really only like a fifth-ish of the story. So here's a page from our paper. And as you can see, I guess the main takeaway is I'm too lazy to stick with the Blackboard theme through an entire presentation. So we're looking at the paper. But this is showing, so this time it takes to actually create the query at the client side for each column is a different number of servers. So there's 4 servers, 8 servers, 16 servers, 32 servers in RAID PIR. This one is how long it takes for the server to respond, so that's what I just showed you. This is how long it takes once you get the response for the client to do all the work it has to do to reconstruct the response. This is the upload cost. There's a huge difference there. Ours is logarithmic versus their linear. And then the download cost, and they don't actually look as big as they could because of the log-log plots. These are all log-log plots, so even a small difference means quite a bit. So that 1.3x speed up we saw for respond was the slowest, or the worst we do in comparison. And this is a little bit misleading, but here we see a 45,000 times speed up. A little misleading, I mean, because this grows logarithmically, this grows linearly, and we just sort of picked a billion as a point and said, look, we're 45,000 times faster at a billion, but that's sort of arbitrary. But the trend is certainly meaningful. So across the board, we see big performance enhancements in terms of how much work the client's doing, how much work the server's doing, how much data is being sent over the network, basically everything. All right, so what's the catch here? So this was summed up repeatedly, quite nicely, by somebody you've probably all heard of. So we cannot tolerate any collusion whatsoever. The protocols are inherently what we call one private. If any server talks to any server, bad stuff happens. And no obstruction isn't the normal terminology, but basically the protocols are also not at all resilient to misbehavior by the servers. If a server doesn't respond, you'll actually possibly learn most of your results, but you won't learn the whole thing, and there's nothing you can do about it except run the protocol again or do something that has questionable security and privacy properties. But if you're in this model where you've got a bunch of servers, none of them are colluding, and none of them are misbehaving, then it's fast. Okay. So how does it work? I'm only going to talk about the very basic part of the protocol. This started off, I said I read that paper, I didn't understand that paper, I read the paper again, we thought about it, we came up with our own version was horrific and impossible to describe. It went through multiple iterations and it got to the point where we were afraid it was going to be rejected on the grounds that it's so bloody obvious. So then we had to sprinkle equations and stuff throughout the paper to make it look less obvious. I'm going to present the super obvious version, but it actually wasn't quite as obvious at first as it seems. Okay, so we have a user here who wants to query a database, but it's a big database. And this is going to be really slow because PIR is really slow. So the idea is we're going to roll some dice, and we're going to use the outcomes of the dice rolls to just choose a little bit from each record in the database. You'll notice this last dice roll came up 0. And the database is indexed by 1s. So when it comes up 0, that means you don't even pick anything from that record, nothing. Otherwise, for 2, we just pick, that should be a 3, I guess. We pick the third chunk of data in that record. For L, we pick the Lth chunk. For J, we pick the Jth chunk. For 0, we pick nothing at all. And then we conceptually form a smaller database that just has this piece of each record. Right, so the L here is actually equal to the number of servers that are involved. So at this point, we're basically taking the database that had a whole bunch of bits, we're compressing it down to less than 1/11 that many bits, and I say less than because about 1 in L plus 1 dice rolls is going to come up 0, and then we don't even include those bits. And in the other places, we include 1/11 of what used to be in that record. And then the client takes this outcome of this dice roll. He replicates it, and then takes the one column corresponding to the record that the client is looking for, and just alters the outcome of that dice roll to span over every possible outcome of the dice. So we're going to have J, and then we have J plus 1, then J plus 2, and it turned out that J plus 3 is 0 mod the number of servers, so this is a 0, and then we start again at 1, and we send a different one of these dice rolls to each of the servers. So because the rolls were completely random, they can't actually tell which one we've altered. If any two of them talk to one another, they can clearly identify which dice roll doesn't agree. The whole thing will be identical except for that one dice roll. And the other thing to note is, so we're spanning every possible number in that one column, so in that one row of the original database, except for here we're actually excluding that. So now from here, the client or the servers just conceptually compute their tinier database. They sum up everything in that database, so they just sum all the columns together. They send the results back to the client, and then the client uses that one that excluded the row he was looking for and ends up subtracting off all of the noise from every other column, and what pops out at the end is the data. So that's the basic idea in a nutshell. In the paper, we have some nice formal definitions. We phrase this as a full, big family of different protocols with various costs. And we have some really clever tricks involving DPFs that I didn't talk about, but they're actually the best part of the paper, and you should totally read it for that part alone. And with that, I'll take questions.
Thanks.
Uh-oh.
Thanks. So you said that in the 2-server case, your protocol is basically
It is. It's not basically, it is, yeah.
So, but how is that? Because yours will be, so that's not rate.
So when you roll the dice, it either comes up 1 or 0. If it's 1, you include the whole record. If it's 0, you include nothing. And then for the one row you're looking for, you send the version with a 1-to-1 server and the version with a 0 to the other server. It's exactly the same protocol. It's just phrased slightly differently.
So it's not rate optimal then? So is your rate optimality?
No, that actually turns out to be rate optimal. When there's only 2 servers, that's the best you can do.
But you get back twice as much data as a record.
Yes, and in general you get L over L minus 1 times the size of a record.
So
that's the rate. So in that case, that is the best that's possible. As the number of servers go up, the thing converges to the size of a record in it. If you end up taking the number of bits in a record plus 1, you have that many servers, then you get the 1 extra bit of download, and then you can't do any better than that.
Right, thanks.
Hello?
I think it's just for the streaming.
Oh, okay, all right. Yeah, this is really interesting. Did you think about the trade-offs that you would make if you were to introduce collusion or misbehavior, and how that would impact the protocol?
Yes, we did think about that. Nothing about that is in this paper, but we have some ongoing work where we're looking at both that and the idea of taking this protocol and introducing batching, which turns out to be basically the same technique. So we're not quite sure how to do I'll leave this on for now. We're not quite sure how to do the rate optimal thing. I didn't mention, but there's actually a nice proof that says you can't do better in terms of computation cost, like the number of bit operations that you do than we do. And we have a protocol and a conjecture that I'm 99.9% sure will turn into a theorem that says that we can basically have the lowest possible bit operations for any non-collusion threshold. But we can't do that simultaneously with the lowest possible download cost, and we're still trying to it seems like it ought to work, but there's some details we still haven't figured out. But yes, we've thought about that, and it'll be submitted soon.
Any last very quick question? Okay, then let's thank Ryan again. Okay, so the next talk is by Raphael on security and efficiency trade-offs in searchable encryptions.
Thank you very much. So
as you've seen, this is a Beamer template, so we're going to jump into more theoretical stuff. I'm sorry if you want something applied, but let's talk about lower bounds and proving these lower bounds on searchable encryption. So again, very quickly, what is searchable encryption? The thing is that we want to outsource some data to some kind of untrusted server. We want to have some search capabilities, so we want this search operations to be fast. Like we really would these operations to be made in a time that is sublinear in the size of the database itself. And to do so, we do allow some kind of linkage. We do allow some information to be learned by the server. And actually, all the security definitions are parameterized by this linkage. Right, so this is a very general introduction, but I mean, we've seen a presentation about that yesterday, so I'm not going to spend more time on this. But the main point here is that the whole field is about a trade-off between security and performance. And what's very, very annoying is that you're not going to get both at the same time. Like, the only place where there is free lunch is essentially security conferences, not searchable encryption. And this is sure kind of frustrating. So first, what do we mean by efficiency? So you have many different measures that you can take to actually state that something is efficient. You can look at the computational complexity, you can look at the communication, you can look at the number of interactions between a client and a server. You can look at the size of the encrypted database, at the size of the client state, and even, so there is a very nice and very cool line of work these days on the locality of the memory accesses you're going to make to search a document among an encrypted database. And actually, there have been some lower bounds, some very hard lower bounds on these things. On the other side, about security, we can look at two ways to evaluate the security. First, we can look at the formal definition of the security by actually looking at the leakage in the security proofs, because all these constructions are often proven in some security model that introduce this leakage function. Or we can look at the security practically from actual attacks. So there have been these leakage abuse attacks where you use this structural information that is leaked by the schemes to retrieve either the queries or even the encrypted database. So here we're actually focusing on the first point. We're doing theory, so we have to be a bit formal. I'm sorry about that, but still. So here in this work, we've shown two lower bounds. One lower bound on the efficiency, and by efficiency I mean the complexity of the client and the server of static searchable encryption schemes. So that means schemes whose database don't evolve in time. And these schemes must hide the repetition of search queries. So if you have a set of searches, and then you have, I don't know, the first and the 12th search query that repeat, then these schemes hide this information. And we have another bound on dynamic searchable encryption schemes. So in that case, we can do some updates. And we focus on schemes that do forward private updates. So I will define what forward privacy is, but essentially you have oblivious updates. So these updates don't reveal any information about the updates themselves. Okay. So first, we restricted ourselves to symmetric searchable encryption. So we're not looking at public searchable encryption or anything like this. So we have a client who is also the data owner, and we have the server who stores the encrypted data. Then we're only looking at single keyword search queries. I'm pretty much convinced that these results can be extended to a more general setting, but here because it's easier to formalize, we're only looking at single keyword search. And another important thing is that we suppose that the database structure, the encrypted database structure, is very specific. We suppose that like you deal with some kind of atoms that are keyword document pairs. So these information cannot be split. So you don't have some kind of weird encoding of your database. And if you're familiar with the ObliViousRAM literature, we are in this model called the balls and bins model. So balls are the entries and the bins are the locations where the entries are stored. So a few notations here. N is actually kind of the size of the problem. It's the size of the database. It's the number of entries. K is the number of distinct keywords. We're going to denote NW the size of the number of entries in the database that match this keyword W. This AW is something a bit strange we're going to use at the end of the presentation, but essentially it's the number of entries matching W that have been inserted since the very beginning of the word of the creation of the database. Sigma is the size of the client state, and H is what we call a query history. So it's the sequence of the first database, the database at setup, and the set of queries that have been hashed to the database. So it can be search queries, update queries. It's just a single sequence of queries. It's just a really general notation. All right. And in what model, security model, are we going to be in? Well, we're going to use a very like standard but kind of weak security definition, where what we want to hide is like the execution, the difference between the execution of two histories, of two sets of queries, but that have the exact same leakage. So we want to be sure that if we have two sequences of queries that have the same leakage, they cannot be distinguished by any adversary after they're executed by the search reproduction scheme. And in our setting, we only need a non-adaptive version of these definitions. So a kind of very weak setting. So essentially, this is a very quick presentation of the security model. So we have an adversary who chooses two histories, H1 and H0 and H1. And we want to be sure that they have the same leakage. So we have the leakage function L, and when the leakage function L is applied to these two histories, they are identical. Right. And we suppose that the scheme is secure when, after the execution, so we end up having transcripts of the execution of the search and updates protocol between the client and the server. And the adversary is not able to distinguish between those two transcripts. All right. So if we focus on schemes that hide the search pattern, and by the search pattern I mean the repetition of queries, we're going to have a leakage function that is essentially that one. So if we have a database and sequence of search queries, so W1 up to WI, what we're going to reveal is, well, the size of the database and the number of distinct queries. And then for every search, what the search algorithm is going to reveal is the number of results that has been returned by the search algorithm. This is something very general. Unless you have something very inefficient, you're always going to reveal, or almost always going to reveal, the number of results to a search query. And if you look at this, you can see that it is very closely related to ObliViousRAM. In ObliViousRAM, you have something similar, so you do reveal the size of your database, and because the result of each search or each access query is as size 1, well, you reveal the size of the number of results you have. And Actually, a construction that achieves something like this has been called file ORM in previous work. So file ORM is just an ORM where you can access different files, but files are atomic, so you're going to access files as a whole. And as such, you're going to download the whole file and reveal the size of the file. So, and you know that there is this very famous lower bound from Goldreich and Ostrowski that says that if you have a client with state whose state is size sigma and your database is of size n, the communication overhead is at least log n over log sigma. And there are very recent work from this year that shows that this lower bound is tight. All right. So if we basically if we apply this lower bound, because we have to fetch NW results every time you do a search query, we expect to have lower bound of that size essentially. So NW log n over log sigma. And this can be rewritten with the small n in exponents. The point is that we know that when we do a search, the entries are not duplicated. So if you access one entry during one epoch, like during one execution of a single search, you're not going to, there is no point in hiding that you're accessing different entries or not accessing different entries. So you don't have to pay for the full ORM price for every entry you access during the single search. So you do have to hide that you might access a different query or a different entry for, you do have to hide which first entry you access, but you don't have to hide that you're accessing a different entry for the second result. So you don't have to hide among n, you have to hide among n minus 1, and so on. So you end up having something like this. So this is a very, very hand-wavy explanation, but still you might expect to have something better than what we had before, because you don't have to hide all the information. Also, like, the order of the return elements doesn't matter. What you actually want is the set of matching elements, not with any order. So you end up having a binomial coefficient instead of having something with factorials here. All right. So again, this is very hand-wavy. And then you have another nice thing is that now you suppose that the client makes two queries, W and W prime, and those two queries have a different result size. And because they have different result size, the adversary immediately knows that the keywords are different. It is immediate. And because the adversaries already knows that they are different, he knows that the access entries during those two searches will be different. So again, there is no point in hiding that you're accessing different entries. And it means that the number of entries you actually have to consider is not n, but is more like n minus the number of already accessed entries in previous searches. So I'm not getting too much into the details here, but you can discard all the entries that have been already accessed in searches with different search results. And we end up having a bound like that, saying that if you have a static SAC scheme that only leaks the size of the database and the number of distinct queries at setup, and then the number of results during search, then the complexity of the search query for both, like when you sum the complexity for the client and the server, is at least this. So I'm not going to read it out loud, but this is essentially what I showed you, and the log factor here is only an artifact of the proof. Like it should go off if we have a better calculus skills than mine. Okay. the point is that this lower bound is tight. So I'm going to go very quickly over this. Suppose we have a few keywords. So W0 has 2 matches, W1 has 3 matches, and so on. What we're going to do is to create oblivious maps. So you can consider this as oblivious dictionaries with oblivious accesses. And each map is going to store keyword with a specific number of matches. So the first map is going to store keyword with one match, the second one with 2 matches, and so on. So this is exactly what we're going to do. So if you take an example here, the third one is going to store both W4 and W1 because those 2 keywords have 3 matches. And the point is that the complexity of an oblivious map of size n is log square of n. So in the end, the search complexity of the construction is log square of k because if we store the number of matches on the client side, we're going to know which oblivious map to access when we search a specific keyword. Yeah, so this is very hand wavy, but in the end, what we have is that the previous lower bound is completely broken when the number of entries in your database is way larger than the number of distinct keywords, which is a very common case. And the point is that when we do this, we do leak some additional information because of the size of the different oblivious maps. We do leak some information about what we call the database profile. The database profile is the number of keywords depending on the size of the results. And what it means is that if we add a small leakage, then we can break the lower bound. That's the point. So very quickly, for the last 3 minutes I have, or 2 minutes I have, I'm going to go over forward privacy. So forward privacy is a defense against what we call fine engineering attacks. And these are active attacks that allow you to decrypt the entire database or the ask queries if your scheme reveals some information about updated keywords during an update. And the point is that today forward privacy is a de facto standard for dynamic schemes. And there is now a pretty big literature on these type of schemes. And what appeared to me when I started working on this is that it seems that you somehow have to pay a cost for that. Either you do have, essentially you have to have a huge client size. So a client size that is linear in the number of distinct keywords if you want to achieve forward privacy, which is annoying if you want to scale correctly with the number of distinct keywords. And what we showed in this paper is that actually this is a lower bound. There is a relationship between the number of distinct keywords and the search complexity, or the size of the client's state. So essentially, I think the most important part is this. It says that the update complexity is logarithmic in k if your client size is of size 1. So if you have a constant size state, then the update is logarithmic. And yeah, I'm not going too much into details here, but again, the lower bound is very tight, and we just have to apply the previous results that showed that, we already reached the lower bound before. Yep, so this is what I wanted to present, like 2 lower bounds that might not seen as practical results, but are interesting because we know now that we don't have to go a lot further than this to construct, especially for forward private constructions, and like these bounds are essentially tight. Yeah. So thank you. So you can find the slides on my website, and if you have questions.
We have time for a quick question. So can you say something really quickly about sort of what this means for searchable encryption in practice? Because sometimes it seems that you do a lot of work, and in the end it would be faster just to do it locally. Does this mean that it's still possible, or does this push it up so far that we maybe should not try?
No, it's possible, but you have to be aware of what you leak as information. That's very important. Things are practical for real, but if you want to use it in practice, you want to really ask yourself if the kind of information that is leaked is not a threat against the information you're going to store or against the user.
Okay, let's thank Rafael again.